Hi friends, here I am going to present session 4 of paper 7 analysis 2 and algebra 4 of 6th semester mathematics. The topic is functions of a complex variable. So as we know the functions of real variables. So similar to that functions of real variables, here we have to study functions of complex variable. So first we know what is a function. So what is a function? Function is a real relation between two variables, two unknowns. So if we take two complex variables z and w, then the complex variable w is said to be function of the complex variable z if for every value of z in a domain D there must be one or more values of w. So corresponding to each value of z there must be one or more values for w. This correspondence is called the function of complex variable z. It is denoted by w is equal to f of z. Here z is dependent variable, w is dependent variable, z is independent variable. So here for example w is equal to z square. So here for each value of z we get one value for w, and w is equal to 1 by z, and also w is equal to e to the power z. So these are the functions of complex variable z. If w is equal to u plus iv, z is equal to x plus iy, and w is equal to f of z, then this function of complex variable w, that is u and v, are functions of x and y. As we substitute z is equal to x plus iy, so then u and v are the functions of x and y. So we write f of z, functions of complex variable f of z is equal to u of x comma y plus I into v of x comma y. So this is the function of complex variables. Here u is called real part of the function f of z and v is called imaginary part of the function f of z. We have to see some examples on functions of complex variable. F of z is equal to e to the power z. So here by substituting z is equal to x plus iy and using Euler's formula, we write f of z is equal to e to the power x into cos y plus I sin y. So here u is real part, u of x comma y is e power x cos y, and imaginary part is v is equal to e power x sin y. Similarly in example 2, that is f of z is equal to z square, we have x plus iy whole square, that is x square minus y square plus 2i xy. Here u is equal to x square minus y square, real part, and imaginary part v is equal to 2xy. In example 3 also we can see that f of z is equal to z bar is x minus iy conjugate of z. So here u is equal to x, v is equal to minus y. So similar to the real functions, here also we can find limit of a function, limit, continuity, differentiability. So we can see one by one limit of complex function. So as in the case of real functions, so the definition is same. A function, here the function is function of complex variable w is equal to f of z is said to tend to a limit L as z tends to the point z naught if for every epsilon positive there exists delta positive such that modulus of f of z minus L less than epsilon for all modulus of z minus z naught less than delta. So we write this limit as limit of lim of f of z as z tends to z naught is equal to L. So here this relation modulus of f of z minus L less than epsilon means here epsilon is a very small quantity. However small we can choose that. So it may be 1 by 1000, 1 by 10,000, 1 by lakh, like that. So depending upon epsilon we choose delta. So this modulus of f of z minus L less than epsilon means it is very less than the small quantity. So less than small quantity means it is almost 0. So f of z is very close to L whenever z is very close to z0. So this limit is nothing but the closeness of the values, closeness of extreme values. So that is the limit. So here we have some properties of limits similar to the properties in real functions. Here also we have same properties. So limit of f of z plus or minus g of z is equal to limit of f of z plus or minus limit of g of z. Limit of sum is sum of the limits. Limit of difference is difference of the limits. And also second property, limit of the product f of z into g of z is equal to limit of f of z into limit of g of z. Limit of the product is product of the limits. Third one, limit of the quotient. Limit of the quotient is quotient of the limits provided the denominator value not equal to 0. If the denominator value is equal to 0, then we cannot define. It's undefined. It's indeterminate. It is infinity. So let us see some examples on limit of complex functions. So evaluate limit of z square minus 2z plus 1 as z tends to 1 minus I. So here we have to substitute, we have to replace z by 1 minus I. We get 1 minus I whole square minus 2 into 1 minus I plus 1. So after simplifications we get minus 1. So which is a finite value. So limit exists. Second example, limit of z tends to 1 minus I z cube plus I by 1 minus zi. So here the limit is limit of z tends to I, here the limit z tends to I. So substituting I cube plus I divided by 1 minus I square. So that is equal to minus I. The I cube is minus I plus I. Here I square is minus 1, minus of minus plus 1. So 1 plus 1, 2, minus I plus I 0. So 0 by 2 is 0. So this limit is equal to 0 as z tends to I, not z tends to 1 minus I. Show that third example, limit of z by z bar, that z bar by z does not exist. So this limit does not exist means the left hand limit, right hand limits not equal. Or here we have to find the limit along x axis, that is real axis. So along x axis y coordinate is equal to 0 and limit along y axis x coordinate is equal to 0. So the along x axis y is equal to 0, the limit z bar by z is equal to, so y is equal to 0, we have only z bar means it is x minus iy, z is x plus iy, y is equal to 0, we have x by x, that is 1. So the limit is 1. Similarly along y axis x is equal to 0, so the limit of z bar by z is minus iy by plus iy, so it is minus 1. So here the limit is plus 1 and minus 1, so they are not equal, limits are not equal, hence limit does not exist. So let us see example 4. Evaluate limit z tends to I z square plus 1 by z to the power 6 plus 1. So if we directly substitute z is equal to I, we get 0 by 0 form, which is indeterminate form. So we have to remove that, we have to eliminate that indeterminate form by factorization. So here z is equal to I is a root of both numerator and denominator. So we have to rationalize, we have to factorize z square plus 1 and also z to the power 6 plus 1. So z to the power 6 can be written as z square whole cube plus 1 is 1 cube. This is a cube plus b cube formula. So we write a plus b into a square minus ab plus b square. So z square plus 1 cancel. After this we have to substitute the limit z is equal to I. So we get 1 by 3. So which is the required limit of the given problem. In example 5, you have to find the limit of z square by z to the power 4 plus z square plus 1 as z tends to e to the power I pi by 4. So here we have to use e to the power I pi by 4. Euler's formula we have to apply here. So after substituting the limits, we get e to the power I pi by 2. I pi by 4 whole square is I pi by 2. 2 cancel. 2 2s are 4. So it is I pi by 2. Similarly, e to the power I pi by 4, 5 by 2, 5 by 4 whole to the power 4 is 4 4 cancel. It is e to the power I pi plus e to the power I pi by 2 plus 1. So as we know, by using Euler's formula, e to the power I pi by 2 is cos pi by 2 plus I sin pi by 2. Cos pi by 2, cos 90, it is 0. Sin 90, 1. So it is I. Similarly, in denominator, e power I pi, that is cos pi plus I sin pi. Cos pi is minus 1, sin pi is 0. E to the power I pi by 2 is, it is sin pi by 2 is 1, so it is I plus 1. Minus 1 plus 1 cancel, it is I by I, that is equal to 1. Thank you.